So we're going to start with random samples today. So think about what a random sample would be. I mean, maybe if I took everyone's student ID and I put it in a bag and I shook the bag up and then I randomly selected 5 IDs, that would be like just a random sample. There's different types of sampling methods. Voluntary sampling. A lot of times whenever you buy something, say even from Sonic or McDonald's or somewhere like that, whenever they give you the receipt, they'll say there's a survey on the back. If you fill it out, you'll get a free drink next time, So things like that would be voluntary, Sometimes they give you some type of incentive to do it, but still, that's voluntary. Every once in a while, I get a call on my phone and someone will ask, do you have a few minutes so I can ask you a few questions, a survey on this or that? And so if I have time, I will, and if I don't have time, I'll say, no, thank you, I'm sorry. Always be courteous, though, always be respectful and courteous, because someone that's doing that probably, is getting paid very minimal to do that type of thing. So courtesy doesn't cost anything. It means a lot to everybody, okay? But anyway, so let's think about a sample. If I wanted a sample of how hard it is to hit a softball, and I randomly selected 4 people in here, do you think that sample would be useful? Or what are some of the problems that I might run into if I randomly select 4 people in this class and I want to know how hard it is to hit a softball? Well, what if the person's never hit a softball? What if by chance, I'm talking about softballs, which at least at the collegiate level and high school levels, those teams are female. What if my random selection, what if I chose 5 males? I mean, how would they represent hitting a softball? Would they be able to represent the overall population of female softball players? No, they would not. So you have to be very careful if you have, when sampling. Let's say that I wanted to know the idea of a group of conservatives, and I wanted to use that information maybe to help me decide what to do on a certain topic. And I sampled from a population that was more liberal. They would not be able to represent a conservative idea if the people that I mainly were pulling from were liberal. So you have to be careful when sampling. Any type of sample that over represents or underrepresents a population is called sample bias. So a sample is biased if it over-represents or under-represents some part of a population. I guess that may not be spelled right. That wasn't correct English. Sample bias would be spelled like that. All right, a sampling frame would be a list that identifies all members of the population. So not all members of the population of the world or anything like that, but all members of the population that I'm studying. So that would be a sample frame. A list which identifies all members of a population. Okay, a simple random sample comes from a finite population, meaning a countable population, and is one where every possible sample of the same size n has the same probability of being selected. So this comes from a finite population and is a sample in which every possible sample size n has the same probability of being selected. So if I was going to survey 5 people in this class and I took everybody's ID and I put it in a bag and I grabbed 5 of those out of the bag, then that would be a simple random sample, because every time, let's say, and then I put those back, and I shook it up again, and I grabbed 5 more out of the bag, everybody has the same probability of being drawn, okay? Every sample size n would have the same probability of being drawn. That's a simple random sample. Sometimes that can be taken from things like IDs, where the ID number really doesn't mean that much, but it identifies you as a student. So just like phone numbers. If somebody has a list of phone numbers, that's, we all get those calls. It seems like constantly. But if I have a list of numbers that I know that work, and then I just randomly select 20 of those, I'm going to call them, and I'm going to bother them about something, I don't know, maybe not bother them, who knows, maybe I'm going to give them some money, but the chance that I grab, this 20, or if I put those back and I grab another 20, if I don't follow a pattern, if I do it randomly somehow, then that would be a simple random sample. So maybe instead of IDs, I give everybody a number in this class. If I give you a number in this class, and I've done this before, even starting when I first started teaching, I taught junior high and high school, and so if I wanted to, and I've done it here at Colin, if I want to do group work, I'll go around the room, it doesn't matter where people are sitting, and I'll just give everybody a number. I'll say 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. And I'll say all the 1s come up here, all the 2s go back there, all the 3s over here, and all the 4s over here. It's just a random way of doing things. So that would be a truly random, I guess you could say, a random way to create groups. The only problem with that is sometimes people that know each other sit beside each other in class. So, in which to me that would be a good thing, that I was splitting those people up so they just wouldn't be sitting around talking to each other. But that may cause, it wouldn't really cause any bias, but that may cause some issues. Maybe you sit beside that person because you're married to them and you'd rather be in a group with them and work with them. I don't know. Or maybe, you're just really good friends and you work good together, you study together. That would cause a problem if I split you up into groups. But for the most part, that would just be a random way to make a sample. All right, if you, this table here is in your PowerPoint. If you look at the PowerPoints that come with the book. This is another way, a random number table. You could take a table like this, and then you could assign maybe a person or a thing to every one of those. and then randomly select a few. And then that way you don't have anything attached to that person that would identify them or that thing that would identify them. Maybe I want to, maybe I have like 100 cars that I need to check out, that I've made 100 cars. Let's say that I made 100 Lamborghinis and I'm going to sell them, but I want to randomly select 5 of those to check and make sure that all the parts are running and everything is up to specs and up to speed. And I gave each one of those cars a number, and then I randomly selected, 3 or 5 of those, and then that way there wouldn't be any bias. I wouldn't like pick the ones maybe that I had personally done. Maybe I wouldn't pick the ones that some of my coworkers had done, or So there are different ways to get simple random samples. That's basically what this section tells you. And that finishes what a random sample is. The next section is on the introduction to sampling distributions. And you'll find that the first couple of homeworks here in Chapter 9, they're really easy. Some of you may have already even done them. So, they are super easy when it comes to at least getting 100 on them. Probably easier than a lot of the other sections. But it does get a little more involved as you move into Chapter 9, as we go into the deeper sections. The sampling distribution of a statistic is what we're going to look at first. All right, so whenever I say the sampling distribution of a statistic, I'm talking about like a sample mean or a sample proportion or maybe a sample standard deviation. So a sample distribution of a statistic, such as a mean or a proportion, is the probability distribution of all values of a statistic. When all possible samples of size n are taken from a population. All right. So let's say that I had a group of students. All right. These are all of my statistics students. Maybe they're in this one group here. And so a sampling distribution of maybe a mean or something like that would be it'd be every group of size n that I could possibly take from that population. So all of these little groups over here This would represent every possible group or sample taken from this big population. So maybe I have 30 groups here, or 30 people here, and then I want to see how many groups of 3 could I take from that. Then I could do something like 30C3, see how many possible groups I could have, and then that would tell me how many possible groups, how many possible unique groups could I have, right? And so of course it'd be more than I have listed right here maybe, but if you take all of those possible groups of size, whatever I decide in, then that would be a sampling distribution. And then of course with each one of those groups, maybe I'm finding the mean of their test grades, or maybe I'm finding the proportion of students that have above an 80 average in the class, or something like that. But if you take all of the possible, I guess these are like subgroups that make up the big group, then that's a sampling distribution. And then again, it's of some type of statistic, like a mean or a proportion, you know, one of those things that we've calculated, one of those types of statistics. All right, a point estimator. All right, a point estimator is a single value estimate calculated from the sample data. So one important thing is it is a single value estimate. All right, and it comes from the sample data. Which is intended to be close to the true population value. To be close to the true population data. So here's an example of what a point estimator would be. Let's say that I was an administrator at one of the biggest colleges in the U.S. And let's say at that particular college there were 5,000 statistics students. Okay? I don't know if you know or not, but at some schools, classes, they're not going to be that big, but I know at Mississippi State they have sections of college algebra with 450. Their Calculus 1 class has, they have several sections with 150 each. And Mississippi State is not a large university. It only has like 20-something thousand students there. So some of the larger universities may have 60 to 80,000 students there. Okay, so if I was an administrator and I wanted to know, you know, how are students performing on a certain test, and I had a standardized test that I made every instructor under me give to every one of their statistics students. You know, so let's just pretend that there were 11 instructors. Each one of them taught a section of 450 students, so I'm around 5,000 students then, and I want to know, I know that they could probably give me the overall mean or average of a test, but what if I took out of those, you know, I have 5,000 students here, and I took a little subgroup of, say, 50 of the students, or let's just say 450 of the students. So I took a group of one section. All right. All of my teachers that I have, I tell them, you have to teach it all this way. Here are the PowerPoints I want you to use. I've already made notes for you. Here are the problems I want you to work out and show your students. All right. And then I take 450 scores and I find the mean. What's the variable I use for the mean of a sample? You remember? X bar. So let's say I found the mean of that sample. Then I could probably say that the mean of my population, so my mu, it won't be the same, but it'll probably be close to that, right? So this will approach this value, but it may not actually be the same value. So, for example, the mean of test 1 might be 80% in the sample. It might be 82% in the overall population. But it's still a good estimate of the overall population. Okay? And sometimes we need good point estimators to estimate the actual or something that's close to the true statistical value of the overall population. Okay? I don't know if that makes sense, but that's what a point estimate is, a point estimator. It is a single value estimate calculated from sample data. And we want it to be close to the true population value. A mean, a variance, and a proportion are all good point estimators, or estimators. So the mean, variance, and a proportion of a sample are good estimators. Okay? So if we have a population mean, there's a population, what is our point estimator that we would use of the sample? It'd be our X bar, right? So from the sample we get X bar. That's a point estimator of our population. All right. The other one that we've covered a lot is variance, right? We went over variance. So if we have a variance for the population, what is a point estimator of the variance that would come from the sample? Do you remember the variable? It was S squared, right? So S squared is a point estimator of sigma squared. They're both variance. It's just that, with a sample, we have S squared. With a population, we have sigma squared. All right, and that finishes this section on the introduction to sample distributions. The next section is on the distribution of the sample mean and the central limit theorem. All right. So the sample mean is what's called an unbiased estimator. All right. Your book says if the average value of an estimator equals the population parameter being estimated, the estimator is said to be unbiased. So the sample mean is one of those unbiased estimators. And I've already told you the sample mean is x bar. So I could say x bar is an unbiased estimator of mu. And that's the same thing as me saying the sample mean is an unbiased estimator of the population mean. So I'll put it up here in words too, of the population mean. Both of those statements are the same. It's just one I'm using variables to represent the words. Okay? And so if the estimator equals the population parameter being estimated, then it's unbiased. All right. The sample proportion, and we haven't went over, I don't believe we've went over the variable for sample proportion. So I'm going to kind of put all this together instead of writing two sentences just to save a little time. So the sample proportion, anybody know how to say this? I'm sure you do, right? Maybe I did go over this a little bit. Not much. That's p hat. All right, so the p's got a little hat on it. All right, so the sample proportion p hat is an unbiased estimator of p. P. The population proportion. All right, so we know this about the mean. We know this about the proportion. The other one, and I know I just told you this, but I'm going to write it down anyway. The sample variance S squared is an unbiased estimator of sigma squared, the population variance. All right. So if we have a larger set of data, so like a population of, consider like a population of infinite size, even though really we can't have an infinite population. If we were to assume a population of infinite size, instead of having to worry about, if we're wanting to know what the, we want to find probabilities that are related to smaller sample sizes that correspond to a larger population size of n, or some infinite size, then instead of just using our sigma or sigma squared value, we have to think about, if we're just wanting to find statistics and probabilities about, say, the mean, then instead of just considering the variance as we do normally, we have a value called sigma squared sub x bar. Okay, and sigma squared sub x bar is equal to sigma squared divided by the square root of n, the sample size. Oh, I'm sorry. Leave the square root off. I'm not used to dealing with this variable as much as I am the standard deviation, and that's why I mistakenly put a square root there. Because if I want to know the standard deviation, this is the variance. How do I get to the standard deviation? I take the square root of the variance. So sigma sub x bar is equal to the square root of all of this. So if I take the square root of the numerator, that's going to leave me with sigma, the standard deviation. If I take the square root of the denominator, that's just the square root of the denominator. All right. So the reason why I'm going over this is because if you remember when we were working on probabilities of the random variables, continuous variables, doing all of that, when we started using our tables, we had to use a z-score to standardize the value. Do you remember what the formula for the z-score? It was z equals x minus mu over sigma. Okay? And that is the formula that you use if you're talking about one value. But if you start dealing with sets of values, like instead of considering the birth weight of one newborn baby, I wanted to know what's the probability that the mean of the birth weight of 50 newborn babies would be over a value or under a value. Then we have to, instead of using this normal z-score formula, I have to plug in this alpha, or this sigma sub x bar in instead. So if we start talking about the probabilities of sample sizes that aren't, we're not talking about just one, we're talking about a sample of 50 or a sample of 100. And believe it or not, that's important in the real world. Okay? So I would say x minus mu over sigma sub x bar, which is equal to x minus mu over sigma divided by the square root of n. So you may be wondering, why is that important in the real world? You know what ergonomics is? Like the study of average values of groups of people is one way to look at it. Do you know why this door over here is the height that it is? Because 99.99% of all people can walk through this door without having to duck down. You know why the seats on trains, planes, think, your car seat. Why are those the heights that they are? They are because that average person can fit in that car or that train or that plane. There was actually and I can't remember where it happened, but there was a ferry, something that carries people across water, that went down because it was not ergonomically, didn't use the right values. Okay? Somebody that designed this ferry, they used the average weight of people like in the 1950s. Well, we as a society have become a lot larger. All right? We weigh more than people did 60 years ago, or 50 years ago. So it was made to support a weight of 30 adults at this certain weight. And then, 20, 30 years later, had 30 adults on there and they weighed too much and the ferry went down. So finding probabilities of means of groups of people is important. Like for elevators too. Have you ever been on an elevator and you get on and then all of a sudden you hear Well, believe it or not, I guess maybe I'm one of the only ones, but I've gotten on an elevator. I guess if you put too many people in there, your weight is too much. So people have to get off. So things like that. Elevators are made to accommodate a certain amount of people that would have an average weight of whatever. Okay? And if we know a couple values about a population, we can figure out, say, the probability that the mean weight of a group of 50 people is over 200 pounds. All right? And we're able to do this because we're looking at this stuff in a different way, using this sigma sub x bar. All right. So this leads into the central limit theorem. So the central limit theorem is a theorem which summarizes the distribution of the sample mean. All right. One of the most important characteristics of the central limit theorem, or features of the central limit theorem, is that it can be applied to populations, which is very applicable to inferential statistics and what people do with studies. Okay. So I've already told you about how we have to alter our z-score formula. Instead of, just talking about one person or about one baby or about one whatever, we can figure out probabilities of groups of people. All right. So let's see if I can find you a problem. So this one doesn't have a lot of meaning. It's kind of a boring problem, but we'll go over it first. And you really have to understand the basics of Chapter 8 and finding those probabilities to be able to do this. So if that's something that's giving you problems, just know this is very similar, but it is a little different because we're looking at sample sizes bigger than just one. Okay? All right. So this says, suppose a population has a mean of 30 and a variance of 25. So I have a mean of 30 and a variance of 25. if a sample size of 100 is drawn from the population, what is the probability that the sample mean will be larger than 31? So larger than is very important. And we're looking for a probability here. So if we're looking for a probability, we're going to have to use our z-score charts. This is the probability that a sample mean, so that x bar is greater than 31. All right, so we weren't given one value directly that we need for our z-score formula. What's that? What's the value that I need that I wasn't given? I have my x. My x is going to be 31. Okay? What was I not given that I need? That's right. The standard deviation wasn't given. Okay? We were given the variance. So our standard deviation is the square root of the variance. So our standard deviation is 5. So we do need to remember that we're not always going to exactly be given everything that we need. Sometimes we have to figure some of those things out. All right. So now we're going to figure out the probability that the sample mean will be larger than 31. Okay? So we need to figure out a z-score. So how do we figure out our z-score? Z equals, it's going to be x, which is going to be, for us, is going to be x bar, because that's the value that we're talking about from the sample. So 31 minus the population mean, 30, divided by, and remember we have this new value when we start talking about samples. See, if a sample size of 100 is drawn. So we have to calculate this in the denominator. Okay? So we know that our standard deviation is 5. It's going to be 5 divided by the square root of 100. Alright, so this is 1 divided by, then that's 5 divided by 10. Alright, so what's that? Flip and multiply, or do it in your calculator. You get what? 2.00. Alright, so this is a greater than problem. So remember what I'm trying to figure out here. I have a z-score now of 2.00. So if I was looking under my standard normal curve, let's pretend that that's symmetrical, then if I'm at about 2 standard deviations to the right of the mean, that would probably be about right here. This is a greater than problem. So we're trying to figure out the area under the curve that is to the right of z equals 2.00. So remember, the way that we do that with our tables is what? We're going to say 1 minus what we get from our table when we look up a z-score of 2.00. Okay? Alright, so here is table A. Table A is, remember, the way that our tables work, it's very important that you understand with the tables now that we're using. They will give us the area cumulative from the far left all the way until we get to the z value that we're looking at. Z values to the left of the center are all going to be negative. Z-values to the right of the center are all going to be positive. You can think of Z-scores like they're standard deviations away from the mean. Okay? So we had 2.00, and we wanted to know the area to the right of that. So for example, if this was 2.00 right here, I want to know the area to the right. So I have to say 1 minus, because I know the area under the entire curve is 1. So I'll say 1 minus the area that the table gives me. So if I go to 2.00, 2.0, and then this column is the hundredth place, 0, I have 0.9772. All right, so I'm going to say 1 minus 0.9772. All right, and that's going to be my probability. Do that in the calculator, you'll get 0.0228. All right, so that's about a 2.28% chance that, and this problem doesn't have a lot of meaning to it because it didn't tell us what these values were, but that the sample mean will be larger than 31. All right. So let me see if I can find us a problem that actually has a little more meaning to it. Maybe one that would be somewhat like the homework that you'll be doing soon. We all love homework. All right, let's work this problem. I want to work this problem because it's about ice cream, and I like ice cream. Maybe a little too much sometimes. Alright, so you'll have one on your homework similar to this. Alright, and you don't have to copy everything down. What I would probably do is just copy down the main variables that we'll be using, the values here. So the cost of 5 gallons of ice cream has a variance of 49 with a mean of $36 during the summer. What is the probability that the sample mean would be less than $37.5 if a sample of 142 5-gallon pails is randomly selected? Round your answer to 4 decimal places. All right, so we want to know the probability that a sample mean would be less than $37.5, or that's $37.50. So that's going to be our X bar. That's going to be our X value that we're going to use, but that's our X bar because it's from the sample. And it tells us if they chose a sample of 142 gallons, 5-gallon pails of ice cream. So the 5-gallon right there, that's just there to kind of throw you off. We won't use the 5 gallons for anything. But we do need the sample size, 142. And since this is a less than problem, remember we're going to take the value that comes from the table. Less than left, area to the left. All right. Now we didn't get the it didn't give us the standard deviation, it gave us the variance. So what's our standard deviation? The square root of 49 is 7. So our standard deviation is 7. So z equals, we're going to say 37.5 minus mu 36 over, and remember, it's not just over the standard deviation. It's the standard deviation divided by the square root of n. And that's because we're working with samples bigger than just 1. This is 142. We're trying to figure out the probability that the sample mean would be less than $37.50 if a sample of 142 pails is randomly selected. All right, so let's see what we get. So 37.5 minus 36 is 1.5. Now there's a little trick you can use if you understand how math works. You can flip the denominator and multiply it times the top, which would mean that I multiply what I get in the numerator by the square root of 142 and then divide by 7. But if you want to do all these calculations separately, feel free. Just know that I would take each one out to about 4 places because we have to round a z-score to 2 places. Okay, so that's a 1.5 times the square root of 142 equals, and then I have to divide by 7. So that's what you should get when you do your calculation, ever how you do it. Okay? All calculators are different. So, all right, so if we round that to 2 places, that's 2.55. And we round z-scores to 2 places. So now this is a less than problem. So I can go to my z-score chart and just take the value that it gives me, because that will give us the area to the left of that z value. So 2.55. And what'd you get? 0.9946. All right, so that means the probability that x bar would be less than 37.5 is equal to 0.9946. So there is a 99.46% chance that if you selected 142 5-gallon pails of ice cream, that their mean would be less than $37.50. All right, let's do another one of these. This one is about something that affects us all at one time or another, I'm sure. All right, the mean weight of an adult is 60 kilograms with a variance of 81. So, mean 60 kilograms. Variance is 81. If 121 adults are randomly selected, what is the probability that the sample mean would be greater than 57.7? So we're looking for the probability that x bar is greater than 57.7. So instead of x minus mu, I'm sorry, instead of x bar minus mu, you want to think about it like x minus mu or x bar minus mu is fine. Just know that your x value in your formula is going to be the sample mean that we're talking about finding a probability of. Okay. So z equals, our x is going to be 57.7 minus mu over, all right, I need standard deviation. So that's what? Sigma square root of 81 is 9. So that's 9 over the square root of n. N was a sample size of 121. All right, so 57.7 minus 60. Then I'm going to say that times, I know what the square root of 121 is. That's 11, right? So times 11, and then divide that by 9. All right, so I got, if I round this to two places, this z-score is negative 2.81. All right, was this a less than problem or a greater than problem? It was greater than. So what I'm going to do is I'm going to say 1 minus the answer that I get, because this is a greater than problem. And the answer that I'm going to get is going to come from the z-score chart. All right, so I need to go to the negative z-score chart, negative 2.81. All right, negative 2.81, I got 0.0025. All right, so 0.0025. So that's 0.9975. All right, so there's a 99.75% chance that if I randomly select 121 adults using these values, that their average weight would be greater than 57.7 kilograms. All right, let's see if I can find one more real quick. Alright, so I need to show you how to work this type of problem really quick. It's almost the same, it's just that it doesn't give us everything we need and we have to figure something out. Okay? You may have a few problems on your homework like this. So I'm going to read through it. The mean cost of a 5-pound bag of shrimp is $46 with a variance of 49. If a sample of 48 bags of shrimp is randomly selected, what is the probability that the sample mean would differ from the true mean by less than $1.8? Round your answer to 4 decimal places. The reason why this is different is because it doesn't give you the mean that we're looking for, or that from the sample. Okay. So we have the mean cost of the shrimp, that's mu, that's 46. We have the variance. We all know we need the standard deviation. That's 7. If a sample of 48 bags is randomly selected, what is the probability that the sample mean would differ from the true mean by less than $1.8? Now, differ from the true mean. It tells us the true mean up here. The mean of a 5-pound bag of shrimp is $46. So to differ by less than $1.8, that would mean $1.8 above or $1.8 below. That's not a question, that's a fact. Okay, so to find my x values, I need to add $1.8 to that. So one of my x values is going to be 47.8. My other x value is going to be what? If I add it, I get 47.8. What do I get if I subtract it? 44.2. So what is the probability that the sample mean would differ from the true mean by less than $1.8? So if we can find a z-score for each one of these, what did we do with 2 z-scores before? We found the area between the two, right? And that represents the probability. So we're going to get a z-score on the right side, and we're going to get a z-score on the left side, and then we're going to figure out the area between the two, and that's going to give us the probability that the sample mean would differ by less than $1.8 by saying 1.8 above the true mean and 1.8 below the true mean. Okay, so let's do a quick z-score for each one. So this is going to be 47.8 minus, what was our true mean? 46 over, and I still have to use the new formula, it's sigma divided by the square root of n, and n is 48. Alright, we know what the difference is on the top there because we added 1.8 to get to that number. So 47.8 minus 46 is 1.8. So 1.8 times, I got to do the square root of 48 divided by 7. So that's going to be a z-score of 1.78. Alright, so that's one z-score. Let's find the other one. It's going to be 44.2 minus 46 over 7, or divided by 7 over the square root of 48. Guess what's going to change? The only thing that's going to change is the numerator is going to give me negative 1.8. See, 44.2 minus 46. If it didn't, yeah, negative 1.8. You say that times the square root of 48, divide that by 7, and you get negative 1.78. So to find the area between the two, remember we need to find the area of the one furthest to the right and subtract the area of the one furthest to the left. So let's go to our table, and we're going to look up, it doesn't matter which one we look up first, but let's look up 1.78? Is that what it was? 1.78? So 1.78, I have 0.9625. So for this one right here, the one on the right here, I got 0.9625. Now let's look up negative 1.78. All right, the 8's right there. I got 0.0375. We always say the bigger one minus the smaller one. Okay? And it's going to be the one on the right minus the one on the left. So that's 0.9625 minus 0.0375. So 0.925, so 0.9250 is our answer. So if you have a homework problem that wants to know a probability about your sample mean differing by a value, you have to add and subtract that to the mean that they give you. And that's your two x values. Then use your z-score chart to find both z-scores, and we're finding the area between the two.